Hello and welcome. I'm Anupriya Mathur, Senior Product Manager for Amazon Aurora at AWS. Today we are going to talk about Amazon Aurora Storage Demystified. So we are going to look a little bit under the hood to see how the storage layer within Aurora works. Let's begin. On agenda today, we have what is Amazon Aurora, and then we'll talk about the cloud-native database architecture of Aurora. We'll get into how the Aurora storage grows and resizes itself. How do we achieve durability at such a scale? And then finally about Aurora backups. So what is Amazon Aurora? Amazon Aurora is an enterprise class cloud native database that gives you the speed and availability of high-end commercial databases with the simplicity and cost effectiveness of open source databases. It is drop-in compatible with MySQL and Postgres. What that means is that if you have an app today that works on, say, MySQL 5.6 and 5.7 or 5.7, then it would also work with Amazon Aurora as is. And that's also true for Postgres. And then we have a simple pay-as-you-go pricing for Aurora, and it's delivered as a managed service. Let's now talk about the cloud-native database architecture. That is, what is it that we do differently within Aurora compared to a traditional database architecture? So I'll start with a quick recap on some of the database internals. So databases store data in pages, and these pages are also stored in memory, which we call as the buffer pool. And whatever changes you are making to your data are done in place in this buffer pool. And then databases use the standard do, redo, undo protocol to persist these changes. So a do operation is when you take an action, like for example, if you're committing an order, then that's a do operation. So in case of a do operation, you'll take the old state, you'll do the do operation, and then what you get is a new state and a log record. And then redo is when you have an old state and you have a log record and you redo it to get to the new state. And similarly, undo is when you have a new state and you have a log record and you want to undo the change so you get back to the old state of this. So these log records and the before and after images are stored in a write-ahead log, which is also stored in the durable storage. And then the database instance, from time to time, it would also persist the pages in buffer pool to the durable storage. And that point is known as checkpointing. That is, it writes down the pages from memory to persistent storage at checkpoints. So now let's look at how these log records and checkpointing helps in crash recovery if a crash happens on a database. So here we have two columns. The first one is for pages on durable storage as they get written down at checkpoints. And then we have log records that are also stored on durable storage. And then we have some timestamps, and time moves forward from top to bottom. So let's say we have this transaction 1 that happens, that completes itself. And then there's a log record corresponding to it that will be stored in durable storage. Now note that at this point, there are no pages that are written to durable storage because there's no checkpointing that has happened yet. Then there's a transaction 2 that starts, but in between there's a checkpoint that occurs. So at the checkpoint, the transaction 1, the pages corresponding to transaction 1 are written down to durable storage, but not transaction 2 yet because the transaction 2 has not yet completed. So then the transaction 2 completes and the corresponding log records are written. Then we have a transaction 3 for which also log records are written. And then we have a transaction 4, but when it is running, then at time TF we have a system failure. So transaction 4 did not complete. So now let's see how does the system recover from this. So in order to recover, transaction 1 was already persisted in durable storage, so it's there. But then transaction 2 and 3, to recover from that, the system would use the log records for transaction 2 and 3 and then apply them in order to get to the new state. So it will do a redo operation for transaction 2 and 3. For transaction 4, since it was not done, so it will still use the log records to undo any changes that might have happened because of transaction 4 in order to get the system back to a consistent state. So this is how a database instance would typically use log records as well as checkpointing of pages down to durable storage in order to maintain consistency. And whenever a database is writing down these log records or pages to the storage, it leads to IOs, that is input-output operations on the storage. So if we look at the architecture of a traditional database, it consists of a compute and a storage that is attached to it. So the compute, like we discussed, it is the database instance that does the SQL operations, transactions, and it does the checkpointing, log records, caching, etc. So it's doing all of this, and then when it needs to write these things down, then it would do these IO operations to write the pages as well as log records down to the attached storage. So traditionally, databases have been about IOs. That is, in order to, like, our design principles have also been around making the IOs better by either increasing the IO bandwidth, that is, you broaden the pipe so that you can write more, or you would decrease the number of IOs by techniques such as batching, so that you're doing less number of IOs now. Now, with Aurora, we followed slightly different approach. So with Aurora, what we are saying is that your log is the database. So we say that as long as I have the complete log stream, I can reconstruct any page in my database. So for example, if I have a database starting at time t0, and then it goes up to time t5, and I want to reconstruct the page at time t5, then I can take all the log records from t1 to t5, apply them, and then I get the page at t5. So which means that I just need to maintain my log records and maybe not need to do any checkpointing, right? But this approach had its own problems. The first problem was that relying only on log streams is a bit impractical. Like, for example, if you have a database that is running for 3 years and you want to reconstruct a page which is 2 years old, then like to apply all the log records from time to t0 to up to 2 years is not practical. So then what do? Then it's like we do checkpointing, periodic checkpointing, wherein we update the pages with these log records so that the pages in durable storage are also updated. But that gets us back to the original problem on traditional databases, wherein your database instances are burdened with checkpointing. So they are maintaining these pages in their buffer pool, and then they are writing them down and doing the checkpointing operation for that. So to solve for that, in Aurora, what we're doing is that we push down the checkpointing operation to the storage fleet, which essentially means that the storage fleet will get the log records, but after that, checkpointing and updating the pages is something which is done in storage. It's no more done by the database instance. The second thing that we thought differently about Aurora was that we separated compute and storage from each other. So just like we saw in the traditional databases, the storage is attached to a compute node. But in Aurora, we said that, if you think about compute and storage, they have different lifetimes. So your compute is more volatile, like, it can fail, it can be replaced. Sometimes, customers would switch off their compute in order to save on cost. You can scale it up, scale it down based on your requirements. But when it comes to storage, storage is long lived. That if you have stored something, if you have stored some data, you would want it to be there and available, right? So for that, we separated compute and storage from each other and created a network storage in order to get better at scalability, availability, and durability. So based on these two ideas, first that we have a log-based database, which wherein we offload checkpointing also to a distributed storage, and second that we separate compute and storage. Based on these two ideas, we created a log structured distributed storage system for Aurora that is multi-tenant, which means that multiple customers can have their database on the same storage, and we are not allocating hardware for each customer. Then it's multi-attached, that is, multiple compute nodes can attach to the distributed storage fleet. And then it's purpose-built for databases. That is, it's a storage that understands databases. It understands what a page is, what a log record is, etc. So now let's look at how we talked about IOs flowing from database instances to storage. Now let's talk about how does that work in Aurora. How does an IO come in, and then how is checkpointing or data persistence done? So here we have a database instance, and then we have storage nodes. One of the storage nodes is expanded to explain the process. And then we have S3, which we use for backups. So the first thing is that the database would send the log records down. And when the storage node receives these log records, it would persist them into durable storage. And then it would send back an acknowledgement to the database instance. So till this point, this is a synchronous process. That is, the database waits for an acknowledgement, and once it gets it, then that's all that it needs to know that, yes, the log record has been persisted. After that, from step 3 onwards, it's an asynchronous process. So then the storage node would organize these log records into a sequence. And if it finds that there are any gaps in the sequence, like some log records are missing, then it would talk to its peer storage nodes to find out if the peer storage nodes have received it, and then complete the sequence. Once the sequence is complete, then it will coalesce them and then write the updated page versions. And then from time to time, we also write these log records to S3 for backups. And we would periodically collect, periodically garbage collect any old versions of pages which are no more required. And then there are CRC checks or checksums that are done on these blocks to make sure that there are no data gaps. And if there are any holes found, then again, the storage node would talk to its peers in order to fill those gaps in. And like I said, only the first 2 steps are synchronous, and after that, everything else can be done asynchronously. Let's now get into how storage in Aurora, how does it grow and resizes itself. So a volume in Aurora can grow up to 128 terabytes now, but it doesn't make sense to put 128 terabytes on a single disk, because that would increase our risk on repairing if there are any failures. So what we do is that we split a volume into multiple segments of fixed size each, so that we can have smaller segments in which we are storing data. And thus, if we have any failure, then if we have to recover, then we can recover faster on a smaller segment compared to 128 terabyte volume. But to determine that what should be the right size of a segment, we had to make a trade-off. Like, if we make our segments too small, then we will have many segments, which would mean that the number of failures that can happen would increase, because now you have too many segments. But if we increase the size of the segment, if it is too big, then it's difficult to repair, because you are repairing a bigger size now. So we thought about this, and then we said that let's pick up a segment size that we can recover fast enough. So We cannot always control what failures are occurring, but we can definitely control how fast we can repair if a failure occurs. So based on that and based on our analysis, we found that 10 GB segment size is something which we can recover within a minute. So that is the segment size that we picked for now. So the segment sizes now are 10 GB each. Database resizing. How does your data grow when you how does your database grow when you write data to your database? So starting from Q4 2020, your databases can expand up to 128 terabytes, but that doesn't mean that you're charged for those 128 terabytes straight away. What we do is that as you write data, the volume size increases in 10 GB segments. So it starts at 10 GB, and as you write more, you're allocated more chunks of 10 GB that you can continue to write to. And with that, you can grow up to a maximum of 128 terabytes for a DB cluster. Now, what happens when you delete data? So with our latest releases from Q4 2020 onwards, your database size also decreases when you delete data from your database. Like, for example, if you have a database of 40 terabytes and you delete a table of 10 terabytes, then your volume size comes down to 30 terabytes. And you also pay for 30 terabytes going forward. And this deletion or this decrease in size happens at a page granularity, which means that, for example, if you just delete a single row, which is small enough that it doesn't free up a page, then you won't see that delete immediately. The delete would come in when a page size is freed up, and the page sizes, for example, for MySQL it is 16 KB. So once you have a 16 KB delete, then you would start seeing that delete in. And the delete happens immediately. Like the volume decrease happens immediately as soon as you delete data. It happens within like a few seconds to a few minutes, depending upon the size of the delete. And then finally, you can also monitor how your database size is increasing as you add data or decreasing as you delete data using the CloudWatch metrics called volume bytes used. Let's take an example now to see how your database size is increasing or decreasing as you add or delete data. So here we have a new database which we created, and then you created a table T in that and added some data to it to increase the size of your database. And then also added another table T1 and added more data to T and T1 both, so that your database size increases. Then we dropped table T1, and after some time, we also dropped table T. So let's see how it looks like in your volume bytes used metrics. So here, if you see, we started the database at 2146. So at 2146, the database starts increasing as you add table T1 and table T. As you keep on adding data to it, the volume bytes also increase. And then when you drop the table T1, the size of your volume, the actual size of your volume also comes down. And if you see, the slant is it's pretty steep, that it happens immediately. It's not like it takes a long time, and you can immediately see the change in your volume bytes used. Similarly, when you drop table T, then also you see then also you see a sharp drop, and then your volume size comes down to 0 GB where it was initially. Okay, now we talked about 128 terabytes databases. Now let's talk about how do we maintain durability at such a high scale. So durability is when you have committed a transaction, then it stays committed and the data is available even if there's a system failure or a crash that's happening. So typically, in a database, there are independent causes of failures that can occur. Like, for example, it could be a failing node or disk or switches, which you cannot always control. So a standard solution to that is to use replication. typically you would do three-way replication. That is, you'll have three different availability zones, and you'll copy your data across these three zones. And then you'll use read and write quorum of 2 by 3. That is, if two copies confirm, for example, a write, then you say that the write has persisted. So in a 2 by 3 quorum, what happens if there's an AZ failure? So if a single availability zone fails, then you still have your other two availability zones available, and you can still get your 2 by 3 quorum. So there's no data loss, and you're good. But what happens if there's a AZ plus 1 failure? So typically, having two availability zones failing completely is a rare thing, so we are not taking that example. But within an availability zone, there are again, different things like a node or a disk that can fail. So we're calling it an AZ plus 1 failure. So in an AZ plus 1 failure, one AZ is down, and then there is a local failure that happens within the second availability zone. So in that case, you lose your 2 out of 3 copies. So you lose your quorum, and then you start losing data as well, which is something which you would not want to do in an enterprise class database. So how does Aurora tolerate AZ plus 1 failures? So in Aurora, we do 6-way replication. That is, we still have 3 availability zones, but in each availability zone, we copy the data twice. So there are 2 copies maintained per AZ. And we use a write quorum of 4 by 6, which is, we are using 4 for majority because 3 would have been balanced on both sides. So we use a 4 by 6 quorum. And if an AZ fails, then, we still have 2 availability zones available, and we have 4 copies available, so we are good. In case of an AZ plus 1 failure, we still have 3 copies available, so there's no data loss that happens, and we can build the failed copy from the available 3 copies and then recover write availability. Now getting into backups. So in Aurora, we have 2 types of backups, continuous backups and snapshots. So your continuous backups are incremental backups that back up every change that happens to your database. You can set a retention period of 35 days for your continuous backups, and can recover to any point in time within your retention period. So for continuous backups, what we do is that for each protection group, segments, we take periodic snapshots, as well as we maintain log records at each protection group level. So when you note that it's not at a volume level, but at a protection group level. So when you have to recover, then we can take the appropriate PG snapshots and the log records in order to reconstruct the protection groups that are required for a specific volume. But the manual snapshots, or the snapshots on the other hand, are full snapshots of your volume. That is, and this is something which you can do at any point when you want to take a snapshot. These are maintained as full backups of your volumes, and you can also restore from there. And the snapshots can also be copied cross-region as well as across accounts. And you can also manage them through AWS backups if you're using more AWS services, so that it's easy to manage. All right, well, that brings us to the closure of our presentation here. Here are a few references. So there are two papers that were published on Aurora. So you can go through them if you want to know more details about how it all works. And we also have additional sessions on Aurora that you can attend to learn more about new things that are happening within Aurora. Well, that's all that I had for today. Thanks a lot for attending, and have a good rest of your day. Thank you.